There are 2.3 million stone blocks sitting on the Giza Plateau right now. The average block weighs about 2.5 tons. Some of the granite blocks deeper inside the pyramid weigh closer to 80 tons. They were quarried, transported, and stacked with less than half an inch of error across a base that covers 13 acres in a desert where summer temperatures regularly hit 115 degrees Fahrenheit in the sun. No cranes, no engines, no power tools of any kind. Modern engineers have been studying this problem for over 200 years, and here's the honest answer. They still don't fully agree on how it was done. Some pieces of the puzzle have been solved, others are still open, and a few of the answers that have been found are so surprisingly simple that they make the whole thing even more interesting. This is how they actually built in the desert heat. To understand what the Egyptians were up against, you need to picture the Giza Plateau as it actually was around 2560 BC, when construction on the Great Pyramid began under Pharaoh Khufu. You're standing on a flat limestone shelf about 130 feet above the Nile floodplain. The river is roughly 5 miles to the east. Everything around you is open desert, which means no shade, no shelter from the wind, and no natural water source anywhere close to where you're working. In July and August, the ground temperature on exposed limestone can hit 140 degrees Fahrenheit. The air temperature sits between 100 and 115. If you stop moving water through your body, you die. It's that simple. The Egyptians didn't pick this location by accident, though. The Giza Plateau had 3 things they needed badly. First, solid bedrock. You can't build a 481-foot pyramid on soft sand, and the limestone shelf at Giza gave them a foundation that could handle the weight. Second, proximity to the Nile. During the annual flood season, the river swelled to within about a mile of the plateau, which turned the desert into something that functioned almost like a harbor. And third, the plateau sat directly across from the limestone quarries at Tura on the eastern bank of the Nile, where they cut the fine white casing stones that once made the pyramid gleam in the sun. Now, the workforce question. If you grew up watching Hollywood movies about ancient Egypt, you probably picture thousands of chained slaves being whipped across the desert. That image is wrong, and archaeology has proven it pretty definitively. In 1990, a construction worker accidentally discovered a workers' cemetery near Giza. The skeletons inside showed signs of healed injuries, evidence that these people received medical care. Overseers were buried nearby, indicating a real organizational hierarchy. In 2013, another discovery at Wadi al-Jarf on the Red Sea coast turned up what is now called the Mera Diary, the oldest known papyrus document in the world, written by a mid-level official named Mera, who was overseeing the transport of limestone blocks to Giza. He recorded his team's daily rations, their work rotations, and their supply chains in the kind of detail you'd expect from a modern logistics manager. These were not slaves. They were a paid, organized labor force of somewhere between 20,000 and 30,000 workers at peak construction. And keeping that many people alive in that environment was itself an engineering achievement. The workers' village at Giza has been extensively excavated by archaeologist Mark Lehner and his team since the 1980s. What they found was a settlement built specifically to support the pyramid workforce, with bakeries, breweries, fish processing areas, and cattle pens. The scale of food production at this site is staggering when you start doing the math. Archaeologists estimate the operation produced enough bread and beer to feed around 10,000 workers per day at minimum. The Mera Diary records that his team of roughly 200 men received deliveries of beef, fish, bread, and beer at regular intervals. Not scraps, actual rations calculated to sustain heavy physical labor. One analysis of animal bones found at the site suggests that workers consumed around 4,000 pounds of beef, mutton, and goat per day across the larger operation. That's a supply chain running across hundreds of miles of desert and river, organized and maintained for at least 20 years while the Great Pyramid was under construction. Now, how did they deal with the heat specifically? This is where the Egyptians showed a kind of practical intelligence that gets underappreciated. There's evidence, both from artistic depictions in tombs and from analysis of the workers' village layout, that the heaviest labor happened in two windows: the hours before sunrise and the late afternoon after about 3 p.m. when the sun was lower and temperatures had started to drop. The middle of the day, the worst hours, was rest. Not because the Egyptians were soft, but because they understood that a worker who collapses from heat stroke is useless for the rest of the week. They were engineering the human body the same way they engineered everything else, with an eye towards sustained output over time. Water was managed through a system of wells and canals that brought Nile water close to the site during flood season and through organized delivery teams during the drier months. Workers at Giza were not improvising. They were operating inside a supply system that had been thought through at every level. But keeping workers alive was the easy part. Moving 2.5-ton blocks across miles of desert? That's where it gets interesting. The limestone used for the interior bulk of the Great Pyramid came mostly from a local quarry right at Giza, less than a quarter mile from the construction site. That's the good news. The fine white limestone used for the outer casing came from Tura across the Nile, and the granite used for the king's chamber deep inside the pyramid came from Aswan, roughly 500 miles to the south. 500 miles, with blocks weighing up to 80 tons. The Nile made this possible. During flood season, the river was navigable all the way from Aswan to Giza, and wooden barges could carry stone loads that would have been essentially impossible to move overland. The Mera diary actually documents this process directly. Mera's team would collect limestone blocks from the Tura quarry, load them onto wooden barges, sail north along the Nile, and then west along a canal system that brought them close to the plateau, and then offload them for the final land transport to the construction site. He describes making this trip multiple times per month, with military-level precision about timing and cargo. The land transport is where one of the most interesting archaeological discoveries of recent decades comes in. In 2014, researchers studying tomb paintings from the reign of Jehuti-Hotep, an Egyptian official who lived around 1900 BC, noticed something that had been overlooked for years. In a scene showing workers hauling a massive stone statue on a wooden sled, there's a figure at the front of the sled pouring liquid directly onto the sand in front of it. For a long time, people assumed this was a ritual. It was not a ritual. Physicists at the University of Amsterdam ran tests using replica sleds on sand. Dry sand creates enormous friction against a wooden sled. Wet sand doesn't. Specifically, when sand is wet to about 2 to 5% moisture content, it becomes rigid and smooth enough that friction drops by roughly half. A sled that needed 50 men to pull on dry sand could be pulled by around 25 men on properly wet sand. At the scale the Egyptians were working, that difference is millions of man-hours saved over the course of a 20-year construction project. They weren't mystical. They were applied physicists, and they'd figured out a principle that we only formalized mathematically in the 20th century. Getting the blocks to the base of the pyramid is one problem. Getting them up to their final position, up to 481 feet in the air, is another problem entirely, and this one is still not fully settled. The most popular theory for most of the 20th century was a straight external ramp, basically a giant mud brick slope that workers would drag blocks up as the pyramid grew. The problem is that a ramp steep enough to be manageable would have needed to be nearly a mile long by the time it reached the top, and it would have required almost as much material as the pyramid itself to build. There's no archaeological evidence of anything that large near Giza. A competing theory proposed by French architect Jean-Pierre Houdin in 2007 suggests that the Egyptians used a combination approach, a short external ramp for the lower portion of the pyramid, and then an internal spiral ramp built inside the pyramid's outer shell for the upper portion. This theory explains some architectural anomalies that have puzzled researchers for years, and it's supported by 3D modeling, though it hasn't been definitively proven. The honest answer is that we don't know for certain how they got the upper blocks into place. What we do know is that they got them there, and they got them there with a precision that still raises eyebrows. If you're finding this as fascinating as I did when I went down this rabbit hole, hit subscribe. We cover ancient history, engineering mysteries, and the stories behind how civilizations actually worked every week. Now, back to the pyramid. The Great Pyramid's base covers about 13 acres. Across that entire 13-acre base, the four corners are level with each other to within about 2 inches. 2 inches. That's not a margin of error. That's basically perfection at a scale where any slight tilt in the foundation would have caused catastrophic structural problems as the pyramid grew taller. The pyramid is also aligned to true north within 0.05 degrees. For comparison, the Eiffel Tower is aligned to true north within about 0.1 degrees, and it was built in the 19th century with surveying instruments the Egyptians didn't have. How did they pull off the alignment? The most accepted theory involves the circumpolar stars, specifically the stars that rotate around the celestial North Pole and never set below the horizon. Egyptian priests and astronomers were sophisticated observers of the sky, and by tracking the arc of a circumpolar star and bisecting that arc exactly, you can find true north with a precision that's actually quite reliable. Some researchers believe they used an instrument called a maquette, a sighting tool made from a palm rib in combination with a plumb line, to establish reference directions that were then translated down to the building site. The leveling problem, getting that base perfectly flat, was likely solved with water. The Egyptians cut a grid of channels into the bedrock at the construction site and filled them with water. Water finds its own level, always, and it does so without any instruments at all. By using the water surface in those channels as a reference plane and cutting the bedrock down to match it, they achieved a level base that modern engineers still marvel at. Then there's the mortar. The blocks in the Great Pyramid aren't just stacked. They're joined with a binding material, a calcium sulfate compound that Egyptians developed and refined over generations. Here's the strange part. This mortar is weaker than the limestone it holds together, which means if the pyramid shifted or settled, the mortar would crack before the stone. That sounds like a design flaw, but it's actually a feature. The mortar acted as a lubricant during block placement, letting workers slide and adjust each block into position. Once it hardened, it wasn't just glue, it was a shock absorber. The exact recipe hasn't been fully replicated by modern chemists. We know the basic chemistry. We don't know every step of how they made it. That's not a small thing. We have been trying to reverse engineer their mortar for decades and haven't completely done it. You can have all the right materials and all the right techniques and still fail if the operation isn't organized well enough to execute consistently over 20 years. The Egyptians built that organization. Excavations at the workers' village have turned up evidence of named work gangs, groups of workers who competed with each other and took pride in their output. We have actual graffiti from inside the pyramid's construction joints with gang names like Friends of Khufu and Drunkards of Menkaure. These weren't random labels, they were team identities, the ancient equivalent of a company culture built around friendly competition and collective pride. Above the work gangs was a hierarchy of overseers, master craftsmen, engineers, and scribes. The Mera diary gives us a window into what the middle management layer looked like. Mera was essentially a logistics coordinator. He managed a team, tracked their daily work, recorded their supplies, and reported up the chain. His diary entries are bureaucratic in the best possible sense, detailed, consistent, and clearly held to standards by whoever was above him. Workers came in rotating shifts, each shift lasting roughly 3 months, drawn from villages across Egypt. This was a national project in the most literal sense. Estimates suggest that at peak construction, 1 out of every 100 people in Egypt was directly involved in the pyramid project in some capacity, whether building, transporting materials, farming to feed. The workers, or manufacturing the tools and supplies the operation needed. Some scholars have argued that this was deliberate on the pharaoh's part, that the pyramid was as much a social and political engineering project as a construction one. Bringing people from across the country, giving them a shared purpose under the pharaoh's name, feeding them well, housing them in an organized settlement, and sending them home after their shift with stories to tell created something like a national identity. The pyramid wasn't just a tomb, it was a machine for building loyalty and shared culture across a population of millions. Whether or not that was consciously intended, the result is that the Egyptian state developed a logistical and organizational capability during the pyramid building era that made them one of the most administratively sophisticated civilizations in the ancient world. But then there's the question nobody spends enough time on. What happened when something went wrong? About 30 miles south of Giza, at Dashur, there is a pyramid called the Bent Pyramid. If you look at it straight on, it's immediately obvious that something strange happened during construction. The lower portion rises at a slope of about 54 degrees. Roughly halfway up, the angle suddenly shifts to around 43 degrees, giving the pyramid its distinctive bent profile. For a long time, this was treated as a curiosity. Now it's understood as direct evidence of the Egyptians learning in real time. The Bent Pyramid was built by Pharaoh Sneferu, Khufu's father, sometime around 2600 BC. Partway through construction, the engineers realized that the original slope angle, combined with the weight of the stone above, was putting unsustainable stress on the lower structure. Cracks were appearing. The base was at risk of collapse, so they changed the angle, mid-build, on a structure that was already hundreds of feet tall and couldn't be taken apart. This is not a failure. This is engineering adaptation under pressure, and it's a glimpse into how the Egyptians actually got to the Great Pyramid. Sneferu built at least 3 pyramids during his reign, each one more refined than the last. The Bent Pyramid was the second. The Red Pyramid at Dashur, which came after it, was built at the corrected angle throughout and is considered the first true smooth-sided pyramid ever completed. Khufu inherited that knowledge. The Great Pyramid was not a first attempt. It was the product of at least 3 generations of iteration, failure, correction, and refinement. There are also smaller pyramids scattered across Egypt that were started and abandoned, either because the site wasn't suitable, the design was flawed, or the pharaoh who commissioned them died before they could be finished. These aren't embarrassments in the historical record. They're evidence that the Egyptians were operating scientifically, building prototypes, identifying problems, and incorporating lessons into the next project. The Great Pyramid didn't come from magic or mysteries or lost ancient knowledge. It came from decades of getting things wrong and figuring out how to fix them. So go back to that image from the beginning. A plateau in the Egyptian desert, 115 degrees Fahrenheit, 2.3 million blocks averaging 2.5 tons each, a workforce of 20,000 to 30,000 people that has to be fed, housed, organized, and kept alive in one of the most hostile environments on the planet, and a structure that has to be leveled to within 2 inches and aligned to true north within a fraction of a degree. They did it with wet sand and wooden sleds, with water-filled channels cut into bedrock, with a mortar we still haven't fully reverse engineered, with rotating labor shifts and named work gangs, and a logistics official who kept such meticulous records that we can read his diary 4,500 years later. The pyramids don't prove that ancient people had help from forces beyond human understanding. They prove something that I think is actually more interesting. That human beings, given sufficient time, sufficient organization, and the willingness to fail and learn and try again, can solve almost any problem, including ones that still aren't fully understood today. If this video made ancient Egypt feel a little less like mythology and a little more like a story about real people solving real problems, then subscribe so you don't miss what's coming next. We've got videos on the ancient Roman engineering that shaped modern cities, the Bronze Age collapse that wiped out nearly every major civilization in the Mediterranean at once, and the question of why so many ancient structures seem to be aligned to astronomical events. All of that is coming, and subscribers get it the moment it goes live. We'll see you soon.